Other than that, everything I think was okay. We will see. You will get your copies on Tuesday. Tuesday you will get your copy. I have solution and everything available with me, but you will get your copies on Tuesday. If you have any queries, you will see at that time. Okay? Any queries, any questions?
No tutorial.
Cases दिया है ना, when tau 3 is greater than tau 2, when कोई बात नहीं, not required, tau 1 के साथ नहीं चाहिए, tau 2 के साथ नहीं चाहिए. If tau 3 is exactly same as tau 2, then it becomes first order. Then you get directly first order response. When tau 3 is greater than tau 2, in that case you get response similar to first order itself, but you get a over. That is why it is written qualitatively. Remember in the question it is mentioned you have to make those graphs qualitatively. Okay. And the third case is if you are tau 3 is between 0 and tau 2, there also you get a first order process, but you not get a over. But that entire part is only 2 marks. First is the derivation. Okay. All right. Okay, so we will get back to your queries and everything in the next class. And I request all the students to please go through the material clearly. Don't be in a wrong impression or in a wrong illusion that you will be doing. You will be able to do it in the examination. You will not be able to do it. That probably you might have found out now. Isn't it? Correct? Whatever I was saying, maybe you have seen yourself. आदमी हाथ जला के सीखता है ना, जला नहीं होंगे कुछ लोगों ने, ठीक है? तो please go through the material. Don't be in the wrong impression that it's an open book. You will be able to do it. No, you will not be able to do it. It's an open book. Because I don't want you to remember all those formulas, isn't it? That is why it is open. But questions should be, all the questions are new, nothing from the book, nothing from the previous question paper. So everything is fair to everyone, isn't it? Correct? Okay. So let us start with the new topic. New topic is higher order system. So higher order systems are nothing but the systems in which you will get the transfer function. If you look at the denominator of the transfer function will be having a order 2 or higher, more than 2, isn't it? So when we typically get a higher order system, we get a typically higher order system whenever we are having, let's say, n first order systems in series. Typical example is absorption column, distillation column. Typically we have 25, 30 trays are there. Each tray acts as first order system, isn't it? So overall order becomes 25 order or 30 order, isn't it? So whenever we have a stage processes like distillation column, absorption column, that gives rise to higher order system, isn't it? Higher order system and overdamp. You will get overdamp system. Remember, whenever you have multiple capacities in series, you are likely to get overdamp system, isn't it? The second case is processes with date time. So you can see that all the processes usually have some time delay or time lag associated with it, isn't it? Whenever something is changing in the process, your process is not going to respond to those changes immediately. Then there will be some date time associated with the process, isn't it? So whenever processes are associated with the date time, you get a higher order system. Even if you are having a first order system with date time, you will see that it resembles to a higher order system. You will see the next slide. टाइम चेंज हो गया क्या हमारी क्लास का? 2:30 के बाद चालू होता है, सॉरी 10:30 के बाद चालू होता है कि 10 बजे? टाइम नहीं आया करो यार, आराम से कोई कोई आ जाता है एकदम 10:45 को आएगा, फिर वो टीए को परेशान करेगा, सिग्नेचर नहीं किया है। तो प्लीज कम as early as possible, around 10 possible, अगर रात में टाइम सोए हो, ठीक है? ओके, the next case is the processes with inverse response. This we will see. Very often what happens is, whenever we are giving a step input, what happens? My output is also increasing. Correct? For a first order process, my output will be like this. For second order system, I will have a 6-point curve, but the output is going to increase. But there are the cases when you are giving a step input, but your output, instead of increasing, it is decreasing. Instead of increasing, it is decreasing. And that type of system we call it as a system with inverse response. So typically the system with inverse response also gives you a higher order system. Okay, so this is given here. You can see that the higher order system can be represented by a transfer function G0s. Let's say there are n first order processes are there. You have to multiply all their transfer functions, isn't it? And that will give you a nth order system. Correct? Is it clear to everyone? Yes, no? Okay. So this n first order systems in series, this particular case is easy. Isn't it? That anyway we have seen so far. Isn't it? If there are n first order processes, just multiply their corresponding transfer function. Correct? Now let's look at the first order system with a date time. So let's say the first order transfer function we are representing here, and then the date time we have represented separately. Let's say f of t is the input and yt minus td is the output. Remember, in this case there is a date time, that's why this output y is delayed by a time td. Delayed by a time td. Correct? So in this case, if I write down the transfer function of this first order process, what will be that? It will be kp divided by tau ts plus 1. That will be the transfer function of the first order process. Similarly, what is the transfer function of the date time? Transfer function of the date time is e raised to the power minus tds. Isn't it? That is what we have derived earlier, if you remember correctly. Isn't it? So whenever we have a date time, the transfer function of the date time is e raised to the power minus tds. So this particular process which is given in a time domain, I can represent this particular process in a Laplace domain like this. Okay, where the transfer function of the first order process is kp divided by tau ps plus 1, and the transfer function of the date time is e raised to the power minus tds, where td is nothing but the date time associated with the process. So in this case, you can see that actual output in a Laplace domain divided by the input, that will be given by what? That will be given by kp e raised to the power minus tds divided by tau ps plus 1. So this will be the transfer function of the overall system. Isn't it? Now if I represent this particular process, let's say I give a step input to this process. If I give a step input to the process, typically if I give a step input to the first order process, what it gives? It will give a response like this, isn't it? A curve similar to this. This is the typical response of the first order process if I give a step input. But let's say the process is first order with date time. What difference I am going to have if there is a step input? The output will be same. The only difference will be this output is going to shift by a time td. Isn't it? That is what is happening. Here this difference between this blue curve and the red curve, this difference here is going to be td, time td. That means your output you are getting after a delay of time td. Isn't it? So this red curve you are expected to get if you are having a first order process in the daytime. Now this red curve which is starting after the date time td, I can approximately represent this particular red curve by a sigmoidal curve like this, which is shown by a dashed line, black dashed line, isn't it? Where the response is starting from 0, isn't it? But it is very well resembling to a typical response of first order process with date time, isn't it? Correct. And this type of sigmoidal curve, when we are expected to get this typical sigmoidal response, we are expected to get when the order of the system is second or higher. Second or higher. So you can clearly see that the first order process with date time actually gives me a response very much similar to a higher order. Higher order. Do you all agree? Approximately. No, sir, this black curve you can see it starting from 0 time. That is real approximation. It is more like first order, but this date time, whatever it is there, that we have represented, that we have actually this particular date time is there. So actual representation is this particular time nothing is happening. And then this response. Correct. Okay, I will come back to your question again. Okay. Maybe you are looking at it in a mathematically. So mathematically, what will be this e raised to the power t? This term. Phase approximation 1 minus TDS by 2 divided by 1 plus TDS by 2. Now this is the date time you put in this particular equation. What will be the order of S in the denominator? It became second order. Now this is a first order approximation. It's not very correct, isn't it? It's not very accurate. The more accurate second order approximation. If you put this here, what will be the order of the denominator? Third order. Can you see the date time approximation of the date time? You can represent this as a system response equivalent to a second or higher order. I am using this word equivalent primarily because it's not the actual response. It is resembling to that. Okay? Now it is okay. We'll come back. Don't worry. This is very important approximation. Okay. Now, maybe not now, but as we will go ahead, you will understand why this approximation is used. There is a reason why this approximation is used and why we are not solving this equation directly in terms of e raised to the power t. Remember, e raised to the power minus TDS is the actual representation, but we are not solving it in terms of that. Okay, maybe let's try to answer this question right away, not in detail, but at least some information. Okay, if I wanted to find out whether this particular system is stable or unstable, can you say anything on stability of this? Anyone? Stable? You all are saying stable? If you put this e raised to the power minus TDS like this here, in this particular case, then if you put e raised to the power minus TDS in this approximation here, then it will be stable. If you put this, then there is some catch. Okay. So I think we have not discussed that, and as we go ahead, we will discuss क्या हो गया भाई, इतनी नींद कहाँ से आ रही है, इतने जोर से चिल्लाने के बाद भी कहाँ हो? Where you have been? No, you are not there. अच्छा चलो ठीक है, अब वही से शुरुआत करते हैं. बताओ स्टेबल कब रहेगा? हाँ बताओ.
जब रूट्स नेगेटिव होंगे तो स्टेबल.
मजा नहीं आएगा. Not convincing. When the system is stable, when the roots of the denominator are negative, located on the left hand side of the imaginary axis, then the system is stable. Typically, first order process without date time is stable. Typically, second order process without date time is stable. But third order process, will it be stable? Unstable. चलो फर्स्ट ऑर्डर प्रोसेस तो मैं आपको नींद में भी अगर आप पूछोगे तो मैं बोलूंगा स्टेबल है. देयर इज नो डेट टाइम. फर्स्ट ऑर्डर प्रोसेस इज ऑलवेज स्टेबल इफ देयर इज नो डेट टाइम. सेकंड ऑर्डर सिस्टम इज ऑलवेज स्टेबल इफ देयर इज नो डेट टाइम. थर्ड ऑर्डर सिस्टम कैन बी स्टेबल और अनस्टेबल depending on the rules as well as there is some other condition is there that we will see as we will go ahead. There is something called as Bode stability criteria. So if you apply the Bode stability criteria, remember first order process will give you a phase angle of -90. Second order system will give you a phase angle of -180. And the third order system will give you a phase angle of -270. So whenever the phase angle crosses -180, then your system can be stable or unstable. You will not be able to stay. So third order system can be stable, can be unstable depending on the location of the root. There are several other things that involved. Okay. Now in this case you can see that if you are putting this date time, your order can be higher. It's not the second or third. Because this is the approximation. This is still not the accurate representation. So e raised to the power minus CDS. This can give you a higher order system where you might get your denominator, roots of your denominator, which are located on the right hand side. In fact, the date time is one of the most detrimental factor making the system unstable. Okay. First order system, the approaching value of the phase angle is -90. Second order system, the approaching value of the phase angle is -180. But when you are having a date time, the approaching value of the phase angle for date time is -infinity. Phase angle value, approaching value of the phase angle when omega tends to infinity for date time is -infinity. These are the things which we are going to prove as we go ahead. That is why I said this discussion is slightly not correct this time. As we go ahead and as we cover some material on frequency response, then you will understand why I am saying this. Okay. So date time is the most detrimental factor, isn't it? Now the reason why we are discussing here is all these methods are approximating the date time in the form of polynomial. And then the reason why we are approximating in terms of polynomial, because if we approximate in terms of polynomial, we will be able to find out the roots of the denominator and numerator, isn't it? So stability we can find out approximately, though we can find out. Okay. May not be accurate, but some representation we can get. Okay. The correct representation you can get without approximating e raised to the power minus CDS, and that you can do it only by using frequency response. And as we go ahead, we will see the frequency response, and then you will appreciate why the frequency response is at all taught in the process control and why we are not stopping exactly at root locus. Okay. Alright. So now in this case you can see that whenever I am having a date time, in that case the first order system response is going to start at this new time here, isn't it? And approximately we can represent this red line by a typical second order response, isn't it? And that is why we are saying whenever we are having a date time associated with a first order system, it resembles to a higher order. A similar thing is shown here for a second order response also. You can see that typical second order response is shown here. This is for a underdamped system and the red curve is for a overdamped system. But whenever you are having a date time associated with the second order system, you can see that your response is going to start at a new time. And similarly, second order overdamped is going to start at a new time here. Again, this particular response also you can start from here. Isn't it? So So you will have a higher order system in that case. Okay. Remember, whenever the order of the system increases, what impact you get on your output? Your output becomes sluggish and delayed. Isn't it? Correct? Correct. So in this case, you can see that your output is getting delayed. That you can compensate by representing the equation with higher order. Correct? Is it clear to everyone? Now let's move to another important case. This particular case is, remember I said you can get a higher order system if you are having a inverse response. Now this typical example is a example of drum boiler. There is a drum boiler where the water is coming in from the bottom, isn't it? This distilled water coming in the boiler, you are heating this particular distilled water by heat supplied from the jacket here somewhere, isn't it? And because of this heat supply, the water is going to evaporate, it will form a steam, and then steam is removed from the top here. Okay. Now in this case you can see that as the cold water is coming in from the input here, cold water is coming in from the input here. Because the cold water is coming in the boiler, the temperature of the liquid decreases, and whatever the entrained bubbles are there, they also get contracted, and because of that, the level of the liquid in the tank is going to decrease. So in this case, you can see that there will be the boiler tube, isn't it? So here the water bubbles are getting formed, and that will go up. Correct? So as the cold water is coming in the boiler, because of that the temperature of the water is going to decrease, and because of that the level of the liquid will decrease here as the cold water increases. So see, in this case the level depends on how many bubbles are there inside, isn't it? As the temperature of the liquid decrease, what will happen? Whatever the vapor is there in those bubbles, that will contract. So level of the liquid is going to decrease because of that. Is it clear? Now the second case is, so typically this particular phenomena is represented by a first order process in a negative direction. So that is represented by K1 divided by tau 1s plus 1 minus K1 divided by tau 1s plus 1. Okay. Another process here is you are supplying the constant amount of heat, and because of constant amount of heat supplied, constant amount of vapor is getting generated, isn't it? Correct. So here you can see that the temperature of the liquid is increasing because of the heat supplied here, and that will increase the level of the liquid present in the boiler. And that you can represent. Remember, the constant heat supply and constant amount of vapor is generated. Whenever we have this type of thing, what type of process we are expected to get? We get pure capacity process. Remember, we get a pure capacity process when my output is coming from the pump, and pump is going to give you a constant output. So whenever your output is constant, you are typically expected to get a pure capacity process. So in this case, how the liquid level is going to rise if there is a heat input here, that will be given by a pure capacity process, and the transfer function of the pure capacity process is given by K2 divided by S. Correct. Now both these processes are competing with each other. One is the first order process in a negative direction, and this pure capacity process in the positive direction. So both these processes are competing with each other, and there is the input which is F of S. Correct. Now in this case you can see that the output is Y of S. So both these processes are competing with each other. So my transfer function in this case will be what? K2 divided by S minus K1 divided by tau 1s plus 1, isn't it? If I rearrange this particular equation, what I am going to get? K2 tau 1 minus K1s plus K2 divided by S tau 1s plus 1. So overall order of the system is second order, because denominator is having the degree 2 in x. So it is second order. Now the question here is this particular transfer function, whether this particular transfer function is going to give you a inverse response or not. So this particular transfer function is going to give you a inverse response only in case if this first term k2 divided by s is dominating over this first order dynamics. Then only you will get a negative response. Yes or no? Correct. If this first part is dominating on the second, then only you will be getting the negative response, otherwise not. So in this case you can see that you can find out in which condition this first process is going to dominate on the other. So that is possible only and only if, remember here, the roots of the denominator are called as poles and the roots of numerator are called as zeros. So whenever you get zeros which are negative, then and then only you will see that this positive process is going to dominate over the process in the negative direction. Okay. If the question is whether the given system is going to show you a inverse response or not, the answer for that is you have to first find out the zero. And if the zero comes out to be negative, then it's a clear indication that the process is going to have inverse. Okay, so in this case you will get this inverse response. Remember here this inverse response you are getting only if this k2 tau 1 is less than k1. If you have this k2 tau 1 less than k1, you can see that this entire term is going to become, sorry, I said inverse. If you get a positive zero, then you will get the inverse response. Okay. In this case, if this term k2 tau 1 minus k1 becomes negative, then you will have a negative number into s plus k2, and if you equate that to 0, you will have this s equals to positive term. So you will get a positive 0. Okay. So you will get an inverse response only if you are having a 0 which is positive, not negative, one. Okay. Is it clear? Is it clear to everyone? In fact, the tutorial today we will look at similar cases. And this is a very simple case, primarily because we have used here this pure capacitive process. But let's say if I give you a case where there are two first order processes competing with each other, then what will be the condition for negative response, inverse response? In fact, that was one of the questions I have given earlier. So don't expect that to come. If you are having, let's say, two first order processes competing with each other, then also you will have to look at this particular condition, which is positive. You will get slightly different condition here. Instead of k2 tau 1 minus k1, you will have k2 tau 1 minus k1 tau 2. Isn't it? So that means what? If k2 tau 1 is smaller than k1 tau 2, in that case you will get the positive response. Positive 0. In that case you will get a positive 0. Okay. So you can see here, remember initially this dynamics is going to dominate. So this particular term is going to dominate, that's why it is going in a negative direction, isn't it? But as we go ahead, you can see that this particular term will be negating this negative term, and finally, even though the response is going in a negative direction, but finally it will reach to the positive direction when t tends to infinity. When t tends to infinity, the steady state value will be the positive, but initial dynamics will be in a negative direction. Is it clear to everyone? Now the question here is why we are calling this as a higher order. Why we are calling this as a higher order? What will happen if we are, let's say, So see, in this case, this particular figure is shown, which is slightly exaggerated version here. Okay, slightly exaggerated. Okay. Typically, the dynamics which goes in the negative direction will be available only for a very small time. So the actual response will be, instead of this, in a real life case, your actual response will be something like this. Something like this you will have. So this negative part will be very less. In a real life cases, that is what is going to happen. Okay. So if this is the particular case, you can approximate this as so that is the reason why we are calling it as a higher order. Okay. Is it clear to everyone? So basically you can represent this approximately by a sigmoidal curve. That sigmoidal part is important. You will not be able to show by a first order response like this. You will have a sigmoidal curve in any case. Even though it is negative or even if it is not negative, you will get a sigmoidal curve. And sigmoidal curve is a characteristic of what? It's a characteristic of higher orders. Okay. So that is why we are saying that whenever you have a inverse response, it is resembling to a higher order. Even though actually the order of the system might be first order or a second order. But still the overall dynamics, if you look at, it is resembling to a higher order. Is it clear to everyone? Okay. Now moving to another important topic. In fact, this is the most important topic in this particular course. How to analyze the feedback control system. I will only briefly describe that in this talk. Okay. Not look at in detail. So ultimately, what was the aim in this course? To understand whenever there is a disturbance coming into the system, how I can handle the change in the process variable by manipulating the variable so that the impact of the disturbance will be negated. Isn't it? Whenever there is a disturbance coming into the system, I wanted to manipulate the manipulated variable in such a way that finally the impact of the disturbance is negated. Isn't it? That is what the aim is. Correct. So what we are doing, whenever there is a disturbance coming in the system, this disturbance is going to mess up my system, isn't it? And therefore my output variable y is going to change, isn't it? Now in such situation, I wanted to change my manipulated variable n in such a way that even though there is a change in b, I want to negate the change in b by changing n so that y remains more or less same as expected. Correct? Now how we represent this entire dynamics here? So you can see that this is the process where disturbance variables are coming in continuously. I do not have any control on this disturbance variable, isn't it? So what I am doing, whatever the output is coming from the process, that output I am measuring by using a measuring device. This measured output will be Ym. This Ym may not be exactly same as Y, because this measuring device will also have its dynamics. For instance, let's say this is the third type heater system where my output is a temperature, isn't it? This temperature, which is the output variable, I am going to measure by using thermometer. Thermometer is a first order system, isn't it? So whatever the value the thermometer is going to give me may not be exactly the Y, because the thermometer will also have its dynamics, isn't it? So whatever the measured value is there, that is represented by Ym. Once we get this measured value of the variable, we compare this measured value with the set point value. So that is why the minus sign is here, which is associated with Ym, and the plus sign is there with respect to Ysp, which is nothing but the set point. So at this comparator, what I am doing? I am doing YSP minus YM. So YSP minus YM is going to give me the error. This error signal is given to the controller. Now in this case, controller is what? Controller can be proportional controller, PI controller, PID controller, isn't it? Depending on this error value, let's say this is a proportional controller. Proportional controller, proportional to this error, it is going to give you the actuating signal, isn't it? And this actuating signal will be given to the wall. And the wall is going to open or close. So typically this controller is going to give me the electronic signal, and that electronic signal will be given to the wall, isn't it? And that wall will be opening or closing based on that. Typically a stepper motor is put on the top of the wall, and this stepper motor has 360 markings on it, can open from 0 to 360 degrees, isn't it? And depending on the electric signal you are getting, it is going to open by a particular amount. Okay, so that's what is happening here. So this entire process is represented here. So you can see process is a feedback sticker here. Thermometer is a measuring device, isn't it? Controller can be a proportional controller. Proportional controller is going to give that electric signal to a wall. So wall becomes the final control element, isn't it? And based on the opening of the wall, your manipulated variable, which is nothing but the steam flow rate, is going to be changed here. So this is the entire process. So here you can see that D is the disturbance variable and M is the manipulated variable. So M here is the steam flow rate, whereas D is the disturbance variable, which can be a inlet flow rate to the certameter or inlet temperature to the certameter. Correct? Now this entire system we are calling it as a feedback control system. Why? Because first the impact of this disturbance on the system is felt. That we are measuring here. And depending on how much my system is measured up, then we are implementing the corrective action. So it's a feedback system, isn't it? It's a feedback system. We are acting based on whatever the impact the disturbance had on the system. Correct? Is it clear to everyone? Again, this is called as negative feedback. Negative feedback. Not necessary that you will have all the time negative feedback. You can have a system with a positive feedback also. In fact, that type of question I have given earlier. If you replace this minus sign by plus sign here, then it becomes a positive feedback. In that case, the error is not YSP minus YM. The error is YSP plus YM. Okay. More logical here is a negative feedback. But there are some specialized cases where you can also have a positive feedback where this minus sign will be replaced by plus sign. And therefore these signs are very, very important here. If I change minus to plus, your entire equation changes. Okay? Clear? So we will start from this point in the next class. Okay? Alright. So the second system should be dominating over the first. Then at the end we will have a unit. ऊपर से नीचे जा रहा है. हाँ. But then we will not calling like a inverse method. That's not inverse. Why we are calling it inverse? There is a reason why we are calling it inverse. So the critical observation is what? Whenever I am having a positive state, my output should change positively. In this case, it is not happening like that. I am giving a step input, but my output
अरे इस वाले को क्या कर रहा है?